Okay, thank you, Moshe. My name is Cindy Eisner. I'm from IBM. And first of all, I was asked to tell you a little bit about myself. I have a BSc in computer science from the Technion, like from a million years ago, or only 30-some, depending how you count. I worked in writing compilers and in hardware simulation at Intel. You asked me to say, Moshe, a little bit about how I got into it. So compilers were my love, and I got a job writing compilers. And then the compiler department was closed in Intel. It was moved to California. And so I was given the choice of moving to work in CAD for hardware. And it was a little bit scary, all those AND gates and OR gates and flip-flops and whatever, but I got over it. That's how I started working in hardware. I worked for a couple years in EDA in Soran, an Israeli company that no longer exists. And since... It doesn't exist. And since 1994, which is also a million years ago, I've been at IBM. How did I get into formal methods? I was eating lunch in the cafeteria one day at Zoran, and we had a cafeteria together with IBM. And I was late to lunch one day. I wasn't supposed to go in at IBM's time, but I was late to lunch. I forgot to eat. I went in. I saw somebody I knew from Intel, and he said, "Do you want to work at IBM?" And that was Ilan Ber. He was working on formal, and that's how I got started in formal. So I worked in formal methods until a few years ago. I'm still doing it a little bit, but in 2013, I started working on malware analysis. We have a tool that analyzes malware. There's symbolic execution inside, so depending on how you define it, still working on formal or I'm not. So I work at IBM, I work in industry, but we work and we also publish, so you don't have to read what these papers are, but just to say, we've written papers. PSL is a temporal logic used in hardware design, and have a book on PSL with my friend Dana Friesman, who you might have met yesterday. She was here. Okay, what do I mean by I worked in formal methods for a long time? So I mean verification, formal verification, and I mean related stuff. So hardware verification, software verification, verification of protocols, so abstract things that are not specified in a hardware and a software language, and the specifications themselves. Related stuff, checker generation. So we're verifying, say, hardware, and we're formally verifying hardware, but we're spending a lot of effort specifying the design in such a way that formal verification tools can use it. We don't want to waste that effort. So from those formal specifications in temporal logic, LTL or PSL, we generate automatically checkers that also are run during simulation of the chip. Specification languages, optimizing hardware. I'll say a little bit more about it later, and synthesizing clock gating, I'll also talk about it later. So most of the verification and some of the related stuff we do using model checking using SAT, or model checking using BDDs. And then there are some things that are automata theory or logic, or things that are next to that. And I've been at IBM a long time, so I've worked in every single one of these except for checker generation. The main thing at IBM, and there's a lot more, but the main thing we have at IBM for formal is rule-based. We call it the 6th Sense edition. You know, somebody's nodding their head. Excellent. Rule-based is a formal verification tool, a model checker, developed at the IBM Haifa Research Laboratory. When that was our name, now we're called IBM Research Haifa. Very important difference. If you come to work in industry, you'll learn about the important things and the non-important things. One of them is what the place you work is called. Since 1993, So that's a year before I got to IBM, formally verifying hardware. It's been used to verify modules in almost every chip that has come out of IBM in the past, I don't know, 15 years, almost every chip. Before that, some of them. And we also have external clients for the rule-based model checker, for instance, Marvell and Mellanox. So this is what rule-based does. And if you know about model checking, and you probably all do, then it'll be very familiar to you. We take a DUT, a design under test. We take the environment. We take assertions. We put them into rule-based, and we get out solved or unsolved. If it's solved, we get back failed with a counterexample. If it's or passed, and then two kinds of passed. If somebody's heard of vacuity, who's heard of vacuity? Some people. Okay, if you've heard of vacuity, then we can get back either passed vacuously, which means it's passed, but in an uninteresting way. Okay, like every request gets an acknowledge, passed, but there have been no requests. And of course, it's more complicated than that, but that's the idea. So you get back passed vacuously and an explanation, or passed and a witness. And if it's unsolved, then we tell you how many have proven cycles if we're doing bounded model checking or something like that. Okay, everybody knows that model checking has a size problem. So before we start rule-based, or before rule-based starts its main activity, we have reduction engines. We're just looking for a model that is smaller than the model we are checking, but the same formulas hold on it. So there's quite a number, and I'm not going to go into it. Can talk maybe about a little. Sequential redundancy removal. So sequential equivalence is when we have two signals that they are the same when visible at the output, but it could be that the logic that drives them at various times is comprised of latches that behave differently. So two implementations of different logic, and two different implementations of the same logic, and only at the outputs do they become equivalent. And for many reasons, in real hardware, you will have sequential redundancy, but for model checking, it doesn't matter. So if you can do a pre-processing and get rid of that ahead of time, that's a good thing. And there's a lot more stuff that we can do. And the point is not each one that we do, but the fact that there's a lot you can do that's minimizing a model that doesn't actually do the model checking. And then we have various solver engines. So discovery is what we call the very original SMV, Ken McMillan's SMV from 1990-something. And we still have BDD-based engines, and they can still be very, very effective for certain problems. Okay, so we have BDD-based bounded model checking, BDD-based reachability, and the original discovery. And then we have some SAT-based engines. So we have the classic SAT-based bounded model checking, interpolation, Ken McMillan, I think, SAT-based liveness checking, IC3, and then some semi-formal engines when we want to get to really big designs. Okay, so before I showed some publications of mine, and just to show that also people who work on rule-based directly published. The yellow is IBM Haifa people, and the non-yellow are either people in the academy or people not at IBM Haifa. Selected publications, there's a long list. Just the point is we do that. 11 people worldwide develop rule-based. 5 of them are in Haifa, and the rest are, I think the rest are in the States, but there might be one in India, I'm not sure. FE verification engineer. So many problems in formal verification are difficult to solve. It requires more than just taking the tool, reading the user manual, and doing it. So we have verification engineers who specialize in that. And 15 to 20, I was told, because it keeps changing. People come, people go. I don't know. 15 to 20 worldwide. In India, in Europe, and in the States. We have 2 in Haifa. And we have approximately, or more than, 100 rule-based users worldwide other than those. And those are mostly hardware designers who are using Formal on their own designs. 7 other people in Haifa who are working on Formal related topics that are not rule-based. So we have a project in soft error detection and verification. If you don't know what that is, I'm going to say like 3 words about it later. Cloud configuration and pricing tool. So I think that's very interesting. So they're selling, I don't even know the word of it. They're selling cloud things, what they sell from IBM. And they have to configure them, and they have to give a price. And for some reason, determining the price is very complicated. If you give the wrong price, you either lose a customer if it's too high, or you lose money if it's too low. So I don't really understand what's going on there, but they're using model checking to make sure that the pricing tool is correct. Pretty cool. And software model checking. I think it's cool because it's like something completely different than what usually we think of when we think about Formal. Okay, some stuff that's not rule-based that we've done. So this is hardware related. This is aiding verification. So we want to verify power gating. Power gating is like what happens when I close the lid of my computer and it goes to sleep. So some of the hardware goes to sleep, some of it stays awake, some of it remembers the state, but it's not exactly working. And when the parts that go to sleep, they forget their state. Okay? Verifying a power-gated design is much more complicated than verifying a non-power-gated design because, for instance, if you're doing only simulation, then suddenly you have all of these X's that get into the simulation because as soon as something goes to sleep, the value of all of the signals that went to sleep are unknown, they're X's. And X, a 3-valued simulation, so 0, 1, and X, is very expensive. It's a lot more expensive than the 2-valued simulation, and they want to try to avoid it if they can. Okay? On the other hand, we can't take a whole chip and put it into Formal. It's too big. So what we did was we broke the problem into steps. We took the original design. It has power gating. We took a simplified design, which is no power gating. The design before they added power gating, or the design as they think it is without power gating, depending how the power gating got there. And we're going to prove that they're sequentially equivalent. Okay, but they're not. They're not sequentially equivalent because when some of the pieces go to sleep, then some of the pieces output X's. Okay, so it's more complicated than I just explained because of that thing. And what we had to do was a compositional verification where each of them kind of in turn kind of coordinate. And if this one outputs its X's, it's going to be okay because it's not going to emphasize this one. And I think I have a thing that says, okay, so we can't prove sequential equivalence is what I said, and if we break it into pieces, the equivalence doesn't hold, I said, and then this is the part I actually want to say. So there's a way to do it. I don't have time to tell you, but it's pretty interesting. We combine model checking with equivalence checking, and as I said, there's also a compositional element there because you've got all the pieces, and you have to make sure that they that you don't have circular reasoning, as is the problem. So there's a paper if that is of interest to anyone. Checker generation, as I said before, you don't want to waste your formal specification. So here's actually LTL, and it goes to model checking. We want it to go to simulation as well. So we translate it into a checker. So a checker, just a state machine in C++ that's run during simulation and can check the exact same properties when things are simulated, right? Everyone knows that formal verification is very important in hardware design. However, you still have to do simulation, because the simulation is the whole chip. You never put a whole chip into formal. Hold on. It's got that little thing. It tells me to wait. Excellent. I'll tell you about the next slide because I can see it. It's about synthesizing clock gating. Okay, what's clock gating? We have a chip, we have inputs, and we have a clock. And the clock goes tick, 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 tick. You have a clock in your processor. Everyone knows when you go to buy a laptop, you got such and such gigahertz, that's your clock. And sometimes we want to put some of the logic onto the clock. We want to put some of the logic onto the clock just because that makes things better. Electrical sometimes, or for timing sometimes. And so what we want to do is we want to find a function that is equivalent to the function that is input to the flip-flop, that has some of the logic on the clock and some of it stays on the flip-flop, and we have to prove that it is, we have to decide it in such a way that the logic that we come out with is equivalent to the logic we started with. Okay, I was going to tell you about some more things, but my computer is not cooperating. It's doing that, and now it won't listen to me. It's just doing that.
Oh.
Don't say that.
Liveness is important.
Liveness is important.
There was supposed to be a question about liveness.
So I'll just tell you one more thing.
I have a question about this slide.
This one. Great. Excellent. Yes.
I'm always confused between this concept of...
Oh, there we go. Go ahead. Ask about the other one. Ask about this one. Go ahead.
It's confusing, this concept with the model-based testing. Because here, what you call checker, is it going to check the property in simulation or in the actual system?
Okay. It could be either one. In this case, I was talking about in simulation, but you could do the exact same thing and test it during runtime. Runtime verification, right, where you have things that are checking as the chip runs, and some kind of error goes off in case it finds a violation. So either one. As soon as you have a state machine, you can put it into hardware and software. Okay, this is clock gating. I told you about it. Okay, so we have a flip-flop and we have logic, and what we want to end up with is smaller logic here, a little bit of the logic on the clock, and it has to be equivalent. Paper, because I don't have time to tell you how we do it. Soft errors. Who knows what a soft error is? Okay, so I will tell you, and then you will know. For many reasons, but let's say cosmic rays is one of them. Also, things coming off of the packaging of the chip. You can, I mean, when we think of logic, we think it's either 0 or 1, but actually in the physical world, it can sometimes like get a cosmic ray, be zapped, and change from 0 to 1 for a small amount of time. Okay, and there needs to be logic inside of the chips that protects against that. Otherwise, the chips would not work. It's a real problem. It's a real problem here on Earth. Chips that go up into airplanes, it's a bigger problem, and chips that go into spaceships, it's an even bigger problem, just because there's more cosmic rays up there. Okay, so this is a project that is done here that kind of combines a lot of stuff in order to formally verify the soft error detection and verification. Okay, so the detection is if there's a soft error, you want something to go off. Like sometimes in a plane, usually they have 3 different processors running in parallel, and they choose each other. They choose the maximum. But if you just let the soft errors happen all the time, then that's not going to be enough. So the idea of the soft errors is to make that choice happen infrequently. So you want as many as possible to correct while the chip is running. So anybody who's heard of error correction code, kind of that's one of the reasons why you would have error correction code. And what we're doing here is there's manual logic that's put into the chip in order to check for these kind of problems. And what we're doing here is we want to make sure that it's actually protecting the bits we intended to protect and actually correcting the right way. So there's a lot of different pieces. They're detecting a parity function using a SAT solver, not model, dedicated SAT solver, not model checking. They're identifying the gates using BDDs. I apologize that I don't know the difference between these two, but they're doing something different. They're identifying the protected logic, which is the third thing, structural analysis. And then finally, they synthesize drivers and assertions, and then they check them using rule-based. OK. Specification languages. Here's a formula in LTL. And in a real chip, we have clocks. And so we don't want to say globally P implies next Q, because there's a clock, and there might be more than one clock. And on the logic, what we want to say is globally, when P in the clock, then the next time we have the clock, we have Q. OK, so in LTL, this is the way we write it. And this is what happens in PSL. So we add a clock operator. And then you can say globally P implies XQ just like you wanted to, but you say what clock is connected to this logic. Another example, we have globally rec implies next busy until done, okay, which is like a simple thing that we all learn. We might want to say something slightly more complicated. We might want to say, if we have a request and after we have an acknowledge, then what does it say? The next time we have an acknowledge, we have busy until done, something like that. OK, so that's complicated to say. And what we want to do is we want to add an operator that says if we have a request, then the next time we have an acknowledge, we have busy until done. So we just want to put some stuff in so that makes it easier for people who want to specify. And we might want to say it like that using regular expression, like kind of syntax. So if we have a request and then we don't have an ACK and then we do have an ACK, then we have next busy until done. OK, so adding operators is like kind of seems a little bit uninteresting because what's the big deal? And the hard part is adding an operator without breaking the logic. What does breaking the logic mean? You could have a formula that looks like it's a liveness formula if you're used to LTL, but it turns out that it could hold on a path and not on an extension of a path. It could hold that just because you made a mistake in how you define the semantics of the operator. You could add an operator and break that and distributes over or. And you can add an operator and break a whole bunch of things. And usually it happens on the corner cases, like what happens on an empty path or what happens on an infinite path. It's always on the corner cases. But the interesting part of the work is defining the formal semantics and then making sure that they don't break the logic. Software model checking. So we did a lot of software model checking, and each one is kind of different. So the formal verification of a page lock mechanism, the formal verification of a firmware project, and this is the most recent one that I very much enjoyed. Seems like I enjoy the things that have to do with financial. I don't know why. So this one is verification of insurance company ICD migration. ICD is just some kind of standard where you go to the doctor and you broke your arm, and so you didn't break your arm in the doctor's computer. You have disease number 6973, whatever. And they changed from one standard to another. And now the insurance companies are going to have to bill, and they're going to get all these new numbers. And they have all of this code that they wrote, and the code is being migrated automatically. But there are a lot of problems in migrating code automatically. Everybody knows it's not trivial. You can make mistakes. So we need to verify that the code before and the code after is going to pay the same amount of money for the same disease. And of course, they didn't just move to a standard where it used to be 976 and now it's 124, because that's not interesting. They moved to a standard where there are some diseases split into two. Some diseases were canceled. I don't know what happens if you had that disease and they canceled it. this verification is very, very important for the insurance company, right? Because they don't want to pay too much money. If they pay too much money, nobody's going to complain. If they pay too little money, then people are going to complain. So they can only lose by having bugs, and they can lose a lot of money. Yes?
If, like you said, there are maybe 10,000 diseases, and you have an old function that can reduce the cost, and you have a new function that can reduce the cost, is it not feasible to just test all of the cases? Like, why do we need formal?
Okay. Okay, good question. First of all, the diseases, the way they say how the diseases map onto each other, one disease here can map onto a lot here, and also the other way around. So first of all, you have to be very careful about defining that. Again, okay, again, it's not just the diseases. It's then how old you are, whether you smoke, who your doctors are, what this, what that. It comes out to something that was challenging, even though the pieces of code were very small, say like maximum 300 lines each. It turned out to be something challenging for formal verification. It's not just this disease, this disease. Part of the challenge, again, was getting the mapping right, okay? These are doctors. They don't really define clearly what it means by this disease is the same as these three, but this new disease is the same as these four, except if this and that. It's the definition is a mess, and if you don't get if you don't get what they meant right, so it's again a kind of a formal definition kind of thing. First of all, you have to figure out what they mean, because they just wrote it down in some kind of a mess. Okay, almost done. We have HVC, Haifa Verification Conference, every year, usually in November at IBM in Haifa. We would love to see all of you there. We have a rule-based university program, so if you're in a university and you don't have rule-based and you want it, please contact us. Just Google rule-based university program and you can find the link. And I was asked to answer this question, theory or practice. Okay, so my only answer is both. Okay, you have to know theory. You can't work in formal verification without understanding the theory. You cannot develop a good tool, and you cannot apply the tool unless you have a good understanding of theory. At IBM, we also like to publish, so that's another good reason to understand what you're talking about. But our work is also practical. The point is to help IBM develop chips, develop software, support its customers. So if you don't know how to code, you cannot work at IBM. That's all.
So if you have a quick questions about the specifics, you can ask now, but we'll postpone the discussion to after all three panelists. Any quick question? Yes.
Slide number 9.
Number 9.
Yeah, okay.
There were more sub-based model checks.
Yes. That is some kind of...
Repeat the question.
Okay, the question was on slide number 9, there were more SAT-based tools or SAT-based engines. We call them the BDD-based engines. Is that an indication of what happens at IBM? It is an indication. There are more SAT-based. There is more use of SAT-based tools because SAT has a larger capacity, and our hardware designers always want to verify as big a piece as possible, and the SAT-based engines are better for that. However, sometimes you get a problem. We still have the BDD-based engines, and the reason is because sometimes you have a problem that it turns out that BDDs are a lot better. It happens in hardware, and also, for instance, the insurance software verification that I was telling you about, we did with BDDs only because we tried it, and BDDs were better. I don't know why. You know, it's hard to say why. That's why we have a bunch of engines.
Thank you very much.
Mm-hmm.
לא כדאי?
יודעים צריך את ה... יש לך את זה? אוקיי.
רק איפה HTML?
יש פה HTML.
יש HTML?
כן, יש HTML.
רק להשיג גם לשים לחשמל, כי אני מקווה שזה
עם ה-HDMI.
זה מאחורה. מצוין. Just let me check them.
It's not worth fighting it.
Not worth fighting it?
No.
Okay. Okay, so good afternoon, everyone. My name is Gila Kamhi. I'm very pleased to be here. First, I would like to thank the organizing committee and Moshe Vardi, Professor Moshe Vardi, a dear friend for 20 years, I guess. So it's a pleasure to be here. So my name is Gila Kamhi. As I mentioned, I am currently leading the User Experience Technologies lab as part of R&D division located in Israel as part of General Motors. So I was asked to give a bit of a background on myself. So my formal introduction to formal was around 20 years ago as I started in Intel as a young engineer, researcher, and this was in mid-95 when there was this big shocking news of FDIV bug, floating point division bug, where Intel recalled all the chips, and this was like around $500 million cost for Intel. So Intel took an action and formed a formal verification group. So I was one of the first engineers who joined it. So in the coming years, I started to lead Intel's model checking activities. So we used Ken McMillan's symbolic model checker, as also Cindy mentioned, expanded it to word level model checking so that FDIV-like bugs will never occur, but you can never guarantee. And we also extended the model checker to support LTL, Intel's proto-formal specification language. I can say the highlight of my FE years was to outlive, actually witness the satisfiability solver's introduction and actually the replacement of satisfiability VDDs by satisfiability solvers made a big change. So we could actually then could scale to industrial size problems, formal methods. So this was a big thing, and I was really happy to see it. In 2000s, I moved from verification validation to more design domain in Intel, more low power design, microarchitectural design. And then more to customer user-facing problems as I joined the perceptual computing division, the use of 3D cameras and creation of new user experiences. And in the last 2 years, I have joined General Motors. And as I mentioned, my main focus currently in our lab, we have researchers which are working on a multidisciplinary domains, cognitive psychology, human factors, artificial intelligence, machine learning, and all in order to define the new autonomous experience. So in all these years, I can say that formal methods helped me shape my career. So whichever problem I face, I found a way to, in a way, leverage from my formal methods background. So in general, I can say that this theory or practice, it affects the way you address problems. So now I would like to, in this talk, mostly focus on what it takes to get human acceptance of autonomous vehicles, self-driving vehicles, and the role of formal methods, formal models, in order to achieve that. So in order to do it, I would like everyone to, I would recommend everyone to read Mobilize last paper, recent paper. It's an amazing paper which actually says, although autonomous vehicles is the next big thing, it may really get into the winter season as AI has in 1990s, because the existing methods, machine learning, data-driven methods, may not really address the scalability, safety, and comfort problems that we need to address in order to get human acceptance. So why is that? First of all, in the new world, what we are aiming is to give our faith, our life, to the hands of a cognitive robot. This is a big deal. So people are likely not to tolerate, in the same manner that they would tolerate a human driver caused fatality, they would tolerate less a machine caused fatality. So in that sense, we need to reduce the risk rate in 3 orders of magnitude. Actually, the number here comes from the rate at which, or the probability that a wing will be detached from a plane. So we need to really stick to very strict safety rules. So in order to achieve it, by using data-driven statistical approaches, we need to drive miles and miles, and each software update, we really need to do, again, online learning. This means like 30 billion miles drive. This is also a big deal. So a formal model-based approach is for sure needed. But in formal, we are looking for absolute guarantees. So absolute safety is not possible. For example, once you have 2 lanes, the car in the center cannot really ensure that it will not crash, because it is not in control of the other car, the C1. The C1 can get into the vehicle's lane. So if we really want to guarantee absolute safety, then we should forbid the car to get out of the parking. But we can learn actually for humans. Humans drive based on a safety notion, based on responsibility. So we do not really look to in mathematical way. We actually follow the safety rules and take responsibility for our driving. So the language that we need to use in order to come up with a driving policy is, again, not geometric or it's not discrete. It is mostly talking about longitudinal and lateral goals. Follow the car in front of you, quickly overtake the car on your left. So it is could be translated into a set of rules and could be easily formalized. We do not need to go to discrete, explicit methods. And then the safety goal is that actually I'm responsible of the way I'm driving. The agent will never make an accident of its own blame. So it is actually creating a new responsibility safety model. So if we go with this space of formal definition, then we can define the lateral and longitudinal goals on one hand, and these are safety goals. A lateral goal example is, my goal is to be in the center of the lane, of a particular lane. Or longitudinal goals could be relative to the position and speed with respect to other cars. The speed target, the speed constraint at a certain point, and here the points could be a junction or a stop line, whatsoever. But also comfort is important. It is not only a matter of not colliding, but we also need to control the aggressiveness level of achieving them, meaning at the jerk level or the jerkiness of the drive or the acceleration or abrupt stops. Although you may be driving safe, you may be driving not in a comfortable way. So we have a goal of achieving both safety and comfort in order to get acceptance. So hopefully I motivated you via Mobileye, a recent paper, that there is place for formal methods in autonomous driving. Now I would like to give you a glimpse of a practical application in GM. And here we are addressing an even harder problem from formal methods perspective. We are talking about the interaction between the car and the human. And the human is the pedestrian, the road user. So currently what we are saying that in the new autonomous vehicle era, first, we need to get the acceptance of the passenger. This is the human we are first and foremost interested about. It has given its faith and life to the car, and so it is captive in the car. And then we need to deal with the acceptance by the road users. Just imagine you are in a pedestrian crossing and you are seeing a car coming towards you and there is no driver. There needs to be a communication language between you and the car in order to understand the mutual intent. So there is a need for an external communication language need in this new era. And once that is achieved, then we can deal with new meanings. Then the car can be our third address. We can use it for entertainment, for meetings, or whatsoever. But in order to get the acceptance, we have to get the acceptance of the human while it is playing two roles. One, we are a passenger, then we are a road users, and in both cases, we need to use a sound, complete, and not ambiguous language, so the mutual intent between the pedestrian, the road user, and the vehicle are understood. And this will take time, but it is a must for the acceptance of the autonomous era and for it not to get stuck into a winter season. So what we are actually saying that in the new era, we are currently surrounded by cognitive robots who are perceiving the world. And we need to have a means of detecting the intent. And this is a very subtle thing. We need to both sense, and it is not only sense and detect that there is a car, there is a vehicle, but what it is up to. And this is not only needed for the acceptance, it's also for the safety reasons. We need to, and also we need to ensure that there is a traffic flow. We need to maximize the traffic flow. The protocol has to be clear. We shouldn't be stuck by giving way to one another. For example, if you have seen the recent press releases of the trials of autonomous cars, one thing that is seen that they are very cautious. So the car can just stop in a pedestrian's crossing, thinking that there's someone that wants to pass, but he is just talking around. So all these deadlock and situations or starvation situations has to be detected. So in order to formalize this external communication language, we are coming with a terminology. So there is a conflict only when there is a shared space. There is a fight for a shared driving space between the human and the car. So then the problem starts. And if this conflict can be actually avoided through the maneuver of one of the agents, either the human or the car, then there is a solution to our problem. If due to the speed or location, there are cases control-wise that this cannot be achieved, then a collision cannot be avoided. Today, this kind of collision resolution, let's say, is being enforced through traffic signs and through policemen, copmen, and so forth. But in the new world, we do not need to have the same signs, and we do not need to have the same rules. So as we go along, I believe the signs on the roads and the language that we are used to will change. So actually, this is the way the city in the autonomous vehicle era will change. So this is, as I mentioned, this is again showing that there is a pedestrian coming and there is a car coming. So based on the actually characteristics of the pedestrian, meaning the velocity in which it is coming, the acceleration that it is coming, its location, and the speed of the car, we can actually know whether the collision is avoidable or not, because there are cases where it is not avoidable. So this is this kind of rules could be again formally specified. So again, here you are seeing also from a famous, very old paper, the green area and the operational regions where the car will, in this area where the car can stop, and in this area, the area that the car will kind of, this is the area where the car will not stop, and from here on, this is the operational area of the car. So it needs to go that distance until it will actually stop. Then in the formal, we always think of the state machines, and the way also when we define a language, we have to think of the regions, the zones, the dynamic regions that are the space that the moving space of the pedestrian and the car, and there are the zones which are static, like the intersection, the junction, traffic lights. So the state of the two agents that we have here, for the sake of discussion, the vehicle and the pedestrian, should be defined in terms of the proximity, velocity, with respect to those zones and regions. So a state of the car could be driving, slowing down, idle, accelerating. And in the same fashion, we can define the states of the road user. So here it's an example of a pedestrian crossing, and the way we are actually formalizing it from the perspective of the car. First, we are seeing that in the first state we are driving, there is no conflict. This is the driving zone, and then there is a passing to the pedestrian crossing zone. So we are driving, we are getting closer to the pedestrian crossing zone, so there's a maneuver of slowing down. And there is no conflict, meaning that there is no road user which is jumping, or road user meaning it could be a human or an animal or whatsoever that is crossing our roads. So we are, in case of the conflict, we are slowing down. And if there is an intent to cross, when we get to the pedestrian crossing, we are stopping. And if there is no intent to cross in the pedestrian crossing, then we can just continue and move on. And we have to avoid the starvation cases. When we stop, there may be a herd of pedestrians passing, kind of abusing, for example, the autonomous vehicle. So it has to, at a certain point, escalate and say, well, stop, I'm now going, and so that the traffic flow will not be actually affected. So in this case, you are seeing a very simple protocol between the car and the pedestrian and the touch point of the pedestrian crossing, so that we have the traffic flow continuing. And here in the same way, you are seeing the same chart in the state chart mode. And again, here we are seeing the states. And again, this is just one scenario of the AV, the autonomous car, and the world, the road users, and the way it is communicating with them while it is getting close to the pedestrian crossing. Driving, slowing down, stopping and giving way. And if there's a herd of pedestrians that is not letting it cross, then at a certain point it is escalating and moving on. So here again, we are all this exercise of formalizing this protocol is in order to define the touch points where we need to communicate, and if the communication is needed because of the acceptance or because of the safety. And here in this case, again, the slowdown and the communication due to the slowdown is needed in order to get acceptance. You would like to understand or know that the car is actually stopping. You are currently do not have a human driver in the car, and you cannot actually watch its gaze or do eye contact in order to know whether it saw you, whether it will be stopping. So from the acceptance perspective, there needs to be a touch point. In the same way, we can analyze each communication touch point and really observe which need, due to which need we need to have a communication. So I will just show you, this is the modeling that we did in 3D world in order to illustrate the touch points. Now looking to a jaywalker case. In the jaywalker case, we do not have the actually a zone. There's no pedestrian crossing, and the car is going autonomously, and this is the operational regions, and there is a jaywalker, so it is giving way, so it stopped. And now again, you are seeing its operational regions, and it is continuing. So in this manner, we are also creating a 3D world where we can, on one hand, design the communication language, and also kind of feel it, how it looks, because it is very hard to build such a world. So I will not go over the jaywalker case again. It's very similar. So if I summarize it, so the design process that we are going for each communication touch point, in order to understand it, we are going over the scenario, and we are actually formally defining it. And this exercise of formally defining the communication need, getting close to a particular zone, whether it is a pedestrian crossing or if it's a junction, helps us to define the touch points where the communication is needed. And once we have identified these cases, we are trying to abstract it out so that there is no redundancy and there is a repeat. And then we have to understand what to indicate and to whom. And there are several different ways that we could do the indication, and this is getting into more the design area, kind of instead of red, green, and yellow of today, we can have different signs and different ways to communicate with the vehicles. So this would be, so there are several different ways that we could address the needs of communication. And now we can do an analysis and evaluation process to choose which one is better than the other. So in summary, what I would like you to take away is, while defining the future of mobility and humanizing the future of mobility, we are working intensely with formal methods to formally define those communication protocols. Actually, there is an ISO standardization effort going on between all the OEMs to define this new language that we will be all living in the next decade or so. And once we define this language, the implementation of that language has to fit both the humans from the perspective that it should be intuitive, they should be kind of feeling good about it. On the other hand, it should be safe. So the implementation also requires an evaluation process. And again, I gave only a few examples like jaywalker or pedestrians. So ideally, all the scenarios will be abstracted, and we will have maybe 20 or 30 touch points max where we are having new signs and of communication. Today we live with a handful of communication touch points. In the autonomous world, we can do even better. And another point is, was from my reference of Mobileye paper, which mostly focused on another aspect of formal verification, its role in ensuring safety, which is also very important. Kind of, we are saying that we have to ensure that there are no collisions, and we said we will be less tolerant for casualties in case of machines. And there also formal models can play a big role while we are designing our systems in context of their cognitive ability, assuming that the sensing is dealt with on the planning side to decide which act we have to take. We can also leverage from formal methods, and as I mentioned, it's a Mobileye paper is a very recommended paper to read. So thank you.
I have a quick question. When I cross the road, when, for example, in US we have, you can turn right even on red, I try to establish eye contact with the driver. When I establish eye contact with the driver, we kind of, I don't know exactly, there is some protocol there, but we see each other, and then I know that the driver, so it's very important to know the driver's song. What is going to be the equivalent of eye contact with the autonomous vehicle?
So there are several different ways that we are trying to do. One is a new lighting mechanism is being put or is being planned on the vehicles. So the vehicle is supposed to, and this is what I tried to show in the presentation, is while it is coming close, it has to say, "I see you." And and here we are getting into the implementation topic of there are several ways of putting a smiley or saying "I see you" or being very subtle, and we do not want to also to pollute the city. So those are more design decisions, but for sure "I see you" is needed both frontal and also for the rear car. Even though we do not use it, we have the brake mechanism, still you would like the vehicle in the back also to know what, I mean, we can do even better than today. The car can say to the rear vehicle, there is a trolley passing. It can just reflect it because it has 360 viewpoints, and the vehicle in the back can understand why you have stopped. So for sure, those are the points that we need to add. This is not needed for safety reasons with respect to the other vehicles, but with respect to the acceptance of the world and safety even of the pedestrians, the way they should be behaving is very important.
Thank you.
We are using it not from the perspective of the formal. We are using it from the perspective of seeing how, as we said, there are several different design techniques that we could use. We are also using virtual reality. Kind of, you can get in and just change your perspective. You can be the passenger, or you can change the role and be a pedestrian, and see how you would feel in those touch points. First, we have to do the formal in order to understand which touch points, and then in order to, in the stages, as I mentioned, in the implementation stage, it's a very hard problem because we do not know what to predict and how this transition period also will be. The hardest portion will be in the transition period when not everything is autonomous. So we have to deal with all this bilingual or multilingual state.
We need to stop here.
Okay.
So, yeah, thank you again.
Thank you. תודה. זה שלי. אני אסדר את זה. זה בסדר. לא שלי. מיקרופון. שנייה.
יש פה עוד חיבור? טוב, תעשה VGA. תעשה VGA.
שנייה.
אין חיבור HDMI?
אז יש את
VGA לך
כן, VGA עובד.
תעזור לי. אני צריך להדליק או משהו? לא. Okay. Hi everybody, my name is Eytan Dreifus. I'm here from Mellanox. Thank you for inviting me to speak. And I've been requested to come and tell you a little bit about how we do formal in Mellanox. Unlike IBM and GM, Mellanox is a little bit less known, so with one sentence, Mellanox is developing end-to-end hardware for high-end communication networks, especially in the industry. We do make networks for supercomputers and for data centers, clouds, these kind of applications. And I'm working on developing these chips, this hardware for these networks. Now you can hear me? Better, okay. So a little bit about myself. I was studied in Tel Aviv University. I have a first degree in engineering and physics. And as a student, I started work in Mellanox. And for the last 10 years, I've been doing formal verification in Mellanox. And in my current position, I am leading the formal verification of our Ethernet switch product line. And this is our latest development, the Spectrum 2. And more than that, I'm in charge of all the formal methodologies in Mellanox. That means how formal is practiced, guidelines on how to make formal the best, in the fastest way, the most efficient way, and how to use it correctly. And aside from that, I review people's work prior to the actual work they do and after. And I'm also in charge of the interfaces to all the tools and scripts teams that we use. Also formal technology and other scripts that make our life easier. So I'll start with telling you what the formal objectives are. So first of all, and most important objective is reaching high quality of our chips. The ability of formal tools to clean all the bugs of the corner cases and the stress tests and reaching a design which is practically bug-free is an important goal. And as a side goal, we also achieve very robust designs. Why? Because the moment the design is clean of bugs and all the corner cases are dealt, the design is cleaner, it's written in a much better way, and it can withstand any future changes and interface changes that might apply later. The second objective is fast convergence. The advantage of formal environments is that they are very easy to build up, very fast to ramp up. We can get running rules within minutes or hours from start of work. Unlike the dynamic verification, which is our simulation-based verification, which can take days or weeks until they have a stable model with tests running and get real results. The reason is we are very independent. We work alone on with our tools, and the DV has a big system that need to sync with and use, and at least for that we are very good. Another thing is that we can write very specific properties that give very high return on investment, the smart properties that clean out large part of the problems in the system and clean out all the initial bugs, all the initial problems from the hardware. Another advantage is that because the formal always gives the shortest path to the trace, the debug is very easy, and designers are favorable with using formal in this stage, because the moment they write the design, shortly thereafter we find most of the important bugs in this stage, and it's all very fresh. We clean it very fast, and they don't have to start debugging 2 months after they wrote the design, start debugging and understand what they did, and clear out all kind of basic bugs. Other than that, we always look where the dynamic verification is less effective. For example, when we're dealing with liveness rules and fairness rules, and maybe areas where the DV decided not to check, and we apply our formal methods there, and together we get a much clearer image of the whole verification process. And also double checking areas where DV is double checking with DV areas of complex logic. We have very big units, lots of logic. Every unit has a few million cells in them, and the logic is very complex, and in many areas we feel that the dynamic verification is not doing a good enough job, and large portions of the chip are covered also by formal. Now a little bit about how we do the process itself. So in Mellanox we mainly do the logical design verification. We don't have many. We have some other applications. Mainly we check hardware design. Formal is involved in the projects, in all the project stages, beginning with the planning, where our formal experts are part of the planning of the microarchitecture of the chip, and understanding where are the places where a formal is needed, where is the complex logic, where we need to apply our tools, and other than that, suggesting tweaks or changes in the microarchitecture to make the design better for formal. If it's, for example, separating pieces of logic, separating hierarchies, introducing parameters to enable us later to reduce the design, reduce the size of design, and handling the size problem a lot better, and so forth. The next stage is where the design is being written and the verification starts. In this part, each formal engineer gets ownership of a couple of units, 2 or 3 units, and they start breaking down into models. Because of the size problem, the capacity, we cannot verify the entire unit as a whole, and we need to break them down into models to make each one more feasible for formal. This is a very important stage, because selecting the correct hierarchies has a great meaning later on the ability to reach our goals and give an okay sign on the unit itself that it's good to go. After selecting the models, each model is looked at, and we start defining the properties that we would like to check according to the needed features. This is also here I think the most. This is most of the work. Okay, taking the environment, writing it, debugging it, understanding what's needed, and defining exactly which properties need to be checked. And here also come the great expertise, because you can take an environment and define the rules in a very straightforward way and not get very far and miss out on a lot of the whole advantages of formal. And you can write smart rules. Still you can change the design by using its parameters to reach a much better ability of the formal tools, formal engines, to cover all the interesting scenarios. And also you have to use the engines and use the correct configurations of the engines to apply to these properties to reach your goals. An important part of all this property definition and writing is to see that in the general, if you look at the big picture, you don't miss out on anything, because you break down into many properties, but all in all they have to cover an entire the entire picture, and it's like a puzzle. Okay, this is also the fun and interesting part. You have to break down all the pieces and still see that it all fits together and you don't have any holes. Each unit in the development has 3 people that work on it. It's the designer, the DV owner, and the formal owner. And they have to work together all the time to see trade-offs, one according to the other, to see which parts formal are very strong and which part DV is very stronger, and to see that together they get the complete verification of the unit, and they all together bring this unit to tape out, clean and on time, bugless, and so it can be used without any problems later. And at the end, every unit has its sign-off. We have a checklist, a list of items that we have to go through to verify that we didn't miss out on anything, to see that there are no missing properties, to see that we've reached our goals in bound-wise in the unit, to see that and to see that the generation is correct, that we don't have any problems in generation, that we didn't limit the state too much. Yes?
One question. So you are talking about that you are verifying hardware.
Mm-hmm.
So do you develop your own engine, or you just resort to commercial?
I'm just getting to that in a couple of slides. And here a little bit on our results. So we've been having formal in Mellanox for around 15 years, but I started work 10 years ago, and I can tell you the difference that's been made throughout these 10 years. If 10 years ago we only handled very small blocks, formal was a marginal discipline that only handled very small hierarchies using BDDs, and didn't have much power, didn't have a lot of effect. Today we cover very large parts of the project. We're very meaningful, and you can see here that in the last 6 years or so we are increasing in our the percentage of the number of bugs we find of the entire project. Up to now that we got more than 50%, we got almost 60% of the bugs in the latest project. That means we are more dominant than the dynamic verification. And introducing formal again in the first early stages with the fast coverage enables us to get to reduce the time to market, reduce the time of development of a chip by a great deal, because we clean out all the small bugs fast. We get there and we get in and we do all the job and clean out all the small problems quickly. When the DV gets the heavy machinery, the big environments, they have a much clearer path to advance, and this is proven to be very good.
What's the breakdown in terms of staffing?
We have more or less for each designer a formal engineer. We are around 40 hardware verification, formal verification engineers in Mellanox.
But what's the balance between let's say the DV in terms of staffing?
A third. A third.
A third is formal?
Yes, more or less. a third is formal, and we get to 60% of the bugs. As I said, it's written here that a formal engineer finds around more or less 3 times more bugs in the project than a dynamic verification on it. So it's very important. And the project managers won't go to tape out, don't agree to go to tape out without a sign off, a clear sign from the formal engineers to give an okay for tape out. More than that, there's always a discussion on where to apply the formal, which it's a limited resource and we need to apply it wisely. And part of my job is to see where the places where formal is more needed, it's more correct to use. Yes. Loud, I can't hear you.
Discovered 3 times more bugs using formal methods compared to dynamic verification.
Yes.
But again, you're talking that first goes formal method, then you apply dynamic verification. Basically, dynamic verification has no chance of discovering the bugs because they were already discovered.
I think, yeah, that's part of, I agree with you, that's part of the reason that we have a lot more bugs because we reach them first, but still, the initial... Well, because the formal work is a lot faster, that's why we reached the bugs first and we cleaned it a lot faster.
No, the question is, do these DV people find the same bugs if they're given the same open?
Yes, but they will take 3 times more time. It'll take a lot longer. And there are certain bugs, the quality bugs, which are a low percentage of the entire bugs found, that the DV cannot find. And vice versa. There are bugs that are system bugs that involve large hierarchies or a few units together that the formal have a hard time finding. That's why it's always complementary. We need both. No.
What do you mean by quality bug? It's like a timing violation or power?
Liveness, for example. Fairness. Fairness is a kind of property that for a DV is very difficult to find. And formal, it's built in the language. It's very, very easy. Okay. More than that, corner cases. If the design has a corner cases that is reached, that it's very rare, then the DV won't reach it. Now you have to understand that DV tests run a very small fraction of a second in real life usage. So these corner cases in real life will be reached, but in the DV test they just don't appear. They can't reach them. Anything else? No, more or less. Okay, regarding the tools. So in the past, Mellanox used the IBM rule-based platform. And in the last years, we've moved to use our internal tools more. We still have the rules platform, but we use it a lot less. And we've developed the internal, for the last 5 years or so, we've been developing our internal tools. These tools are very highly coordinated with our designs. They match our designs. The optimization in the tools are good for our designs, and for our designs we have reached excellent results with these tools. Also, the technology team and the execution team are constantly talking to each other and in communication, reaching and searching for ways to make the coordinated work better, looking for systems, looking for ways to improve the engines and tweak them to match the design better, looking for ways to write the design or the environments in a better way for the engine, and we are in constant improvement on our benchmarks doing this. Another advantage is that once the personnel, the guys who are developing the tools, are sitting next to you, all the problems are solved very fast. All the ideas are dealt with very fast. It's good work together. And there's a big advantage of having the tools close to you. So, as my colleagues have been asked, which is more important, the execution or technology? And
What do you mean by execution? And what do you mean by
execution is what I do. I take the tools and execute with them and use them to execute our chips. Okay, in technology I mean development of the formal tools. So my answer is both. Obviously, you can't have one without the other. If you have good technology, the capacity is excellent. You have a great capacity, but you don't know how to use it, you won't get anywhere. Our designs have millions of cells in them, and if you don't cut off the correct hierarchies, define the properties in the best way, be very creative, and use your expertise to use the engines in a smart way, you won't get very far. You won't clean the designs, you won't find all the bugs. And the other way around, if you have excellent execution, but you have BDD engines which can handle very small hierarchies, it doesn't get the same effect. You can't reach the goals that you want to reach with your formal tools. So the two complement each other. That's it. Thank you. Any questions? Excellent question, but I'm afraid I'm not the person to ask. We're all the time experimenting with different SAT solvers, and I'm not sure what's currently in use. But we all the time experimenting.
To use his one.
No problem. I'll suggest it to my technology team. But we're searching all the time for better SAT solvers and to find the best one for our designs.
You've been talking all the time on the design level that you apply for the methods. What about the actual executors? How do you define that? Now we have model checking tools that you've developed or verification tools that you've developed. They're software. How can you verify them? Your tools.
Yes.
How have you verified them?
We have benchmarks that run all the time and verify that they are consistent to prior instances. Okay, we have large benchmarks. I mean, we are the execution team. We have a lot of examples, and we give these examples to the tools team, and they run them all the time. Every time they make a change, they look for something. They find bugs with these benchmarks.
Also, what are your special considerations in your designs so that you have to develop your own verification tool instead of using like conformal from Cadence or something of this tool?
Instead of using external tools?
Yep. But like things like in IBM, since they have some design consideration that they make high performance chips, so they have their own EDA tool. So I'm wondering what are the spatial design considerations in your company?
I'll tell you this. We're very conservative in our design in Mellanox. Our design looks more or less the same. Now, when you take an external tools, it supports all kinds of designs and all kinds of types. And there's an overhead here, which we don't have. Our tools are specially made for our design. And there's an advantage here.
I know that will be, I'm asking what are the special considerations in your design, or it's a secret to your company?
I'm not sure I know how to answer this question because I don't develop the tools, but we've compared to external tools and our tools are better.
Okay, let's thank Eytan.
Thank you very much.
I'm going to bring your chair, and I'll bring two more chairs for you.
לוותר על המיקרופון? אפשר לוותר על זה?
Or we just move it around?
יכול לסוגר את זה?
אתה יכול...
here, so please. No, so it's easier for you to move the mic.
Okay.
We'll use one mic per question.
Okay,
Is it on?
perfect.
Is it on? Yes. Okay, so this is the part for the open discussion, and just to get things started, I will ask the first question. So for people, think of different people who come either to work on building tools, or people who are going to use tools. What do you need in terms of what do we as educators need to? Should we educate students that they will become effective tool builders or effective tool users?
They need to be creative. Oh, I need a microphone.
Yeah, use the mic. Yeah.
They need to be.
I
Is
think
it
it's
on?
Yeah, yeah. Just hold it close.
Okay. They need to be creative. Just like when you're studying something new in university, you get a problem. Usually the problem is something you haven't seen before for some reason. Either there's a size problem, or it's a new kind of design, or there's a kind of property you want to check that you can't check with your tool and you have to make a new way. So creativity is what is needed.
So from my perspective,
Hold it close. Yeah, just close.
okay.
Closer. Yeah. It has to feel uncomfortable.
It has to be uncomfortable and safe, but safe still.
Yeah.
So from my perspective, it is very important to define a problem. I was on two sides of things. In my formal years, I developed tools, and since it was Intel hardware, I didn't have a clue what we were verifying. And we had special teams who had theoretical knowledge on formal verification that did the execution. But as I moved to different problem domains and tried to apply formal, I think that the big thing or the big buck comes from solving a real problem, a real world problem, and applying the formal methods. And there are a lot there. And I think formal could be what the next big thing, like we said in AI or machine learning, these things came alive after 20 years. And I think in formal also there's a lot of potential, and maybe it is not being explored fully because usually the formal education is very mathematical intense, and we usually do not look to the problem that needs to be applied to. We look to logic, and it's the verification of a logic, and we do not care what that logic is. And I think we can bring more problem domains to schools maybe, and try to apply, and through that maybe develop tools, because we run to capacity issues and so forth.
Thank you. From my perspective, I think someone who's dealing with formal needs to, first of all, understand logic very well, have a very intimate understanding of how designs are built when we're dealing with hardware. And again, like Cindy said, creativeness is very important, and expertise to understand and to know how to deal with the problems and how to address them in the best way possible.
Thank you for the very nice presentations, very interesting. Are there kinds of problems that you find are very difficult to model and verify formally that you have to test in other ways, such as the dynamic verification or other ways?
Okay, I'll start again. Yes. As Eytan mentioned, full chip verification. A full chip will not go into a formal tool, and there is no choice. A full system even more.
What's the next level down? How big? Can you give examples of problems that you can, and the next level that you already cannot?
It so much depends on what is inside of something, right? You can give me a million state variables with a very certain kind of design, and I can verify it no problem. And you can give me 25, and I can't verify it. It so much depends what's inside. That said, in IBM, we usually want to do something called a unit. And a unit would be something logical, and the numbers have just gone from my head. I'm going to let Eytan talk to you about how big a unit usually is.
If I may, instead of a size, if you can relate, for instance, many of the examples that we see, you know, two clients and a server try to compete on some bus or a critical section. Can you give a descriptive example of a large, complex problem that you could solve, and something that you can't? For instance, you know, a car crossing an intersection safely. I assume that this cannot be done. But something which is more than the small toy problems, but that is bigger than the small toy problems, but smaller than the huge thing, that the chip, that the processor computes everything correctly.
I'm going to late, but I'm just going to say that again. What I talked about before, the creativity, is so important because it is. I can't give you an example like that because I can take an example without a bug. Can give me something that works perfectly and it will go through the formal tools excellently. Add one tiny little bug and I can have the size problem because of the bug. So no, I cannot define a problem for you.
That's I would say that's a very interesting question. I think from my experience, the areas where it's more problematic are areas with a lot of combinational logic, arithmetics, which are harder to handle. And again, as larger as these problems are, when they include more states, it's exponentially more difficult. And if you succeed in reducing these problems, then you go a great deal to help the formal tools succeed in solving this.
So I would like to add
closer.
I would like to add from the world that I live in. So I think anything that involves a protocol where there's humans involved, which is unpredictable and it's very hard to model, the challenge is not, as I see it, on the verification scalability. It's more on the modeling, how you would use a stochastic maybe system, or how you would kind of ensure that there are no collisions in a world that there are unpredictable behaviors that you have never seen. So I think on the modeling side also there are very much a lot of challenges when we try to apply these methods to new problems.
So actually, I want to go back to the full chip question. So everybody says, oh, a full chip is way too big. But full chip only makes sense to do if we do full chip properties. And full chip property should be relatively high level and really much of the logic that's underneath should be not, I mean, I will be surprised if there is a full chip property that really depends on, I don't know, how many transistors you have in a chip, like on the billions of transistors in a chip. So if we cannot do full chips, it tells me that our abstraction techniques are not good enough and are not able to somehow cut out all the details that should be irrelevant to that property. And I would think by now we've done it, and you guys have done it for so many years, that you should be able to do full chip.
Yeah, in theory, perfect. Yes, you should be able to write a property, and most of the. First of all, I'm not sure I agree that most of the logic doesn't affect that property. I mean, you might have some kind of a pipeline, and if the pipeline is full, then it's going to act differently than a pipeline is not full. And most of the logic on the chip is going to depend on that pipeline. And then you have the interface to the cache. And then whatever is in the cache, things are going to act differently if, you know, the cache is full, the cache is not full, depending on what is in. Now, yes, if you had a perfect abstraction, you could abstract away the cache, you could abstract away the pipeline, you could do this. And that's what a lot of people do. That's what we did when, we tried to do something like that when we did the power gating work, where we said, okay, we're going to take away the power gating, formally verify them. In theory, that's correct. In practice, I think you're maybe at least 1,000 years away from that.
Wow, 1,000 years. I don't think I have that much patience.
My question is to Cindy. I'm a former IBMer, and I've been following. Oh yeah, sure. I've been following the path of the company this last years, and it seems that at least for the software side, IBM is more into becoming a machine learning, intelligent computing company.
Watson.
Yeah. So my question is, what is the role of formal verification in this scenario?
Okay, wow. First of all, I can tell you that I know there is a new project where we are talking about what it means to verify software, anything in the world of machine learning. Because in the world of machine learning, you have this whole other part, which is what the data you trained on, and what does it mean to be correct or not, and we are thinking about that. We also have a new project, as long as you're going towards the future, in what it means to verify a quantum computer, using regular and using formal verification. So I can't say more than that. Difficult problems, and we're going to think about it.
So it seems from what you all described that really hardware verification is an industrial success and it's a daily practice. What would it take for it to be the same in software verification, if you can speculate?
Software is a lot harder. I think everyone knows that software is a lot harder for many reasons. You've got pointers, you've got the whole memory, you've got... it's a more complicated problem. What would it take? It would take people taking real software and playing with it. Okay, when I started it at IBM in 1994, we were checking tiny little pieces of logic, maybe 100, maybe 500 latches, and abstracting them heavily and sometimes manually and whatever. You can't make any progress unless you try. So what it will take is people trying.
I agree. I think that we have 20 years of methodology on how to practice formal on hardware, which we don't have on software. And evolving this methodology will take a lot of time, and improving the tools to be something that you can use for execution. There's a long way to go there. So once people practice it will take another 10, 20 years, and we will be there also in software.
Gila, you moved from hardware to software, of, right?
But I think it's a bit different. So what I was thinking is, one is software, really the implementation software and the verification of it, which is maybe analogous to the hardware verification. But we could look to the system and define it as a concurrent software module at an abstract level. And there we could apply formal much more easily, using leveraging from the existing tools. And I believe that area maybe I'm ignorant, but I think it is last explored, and this could be very interesting. And again, in reactive systems and aviation or autonomous and all those kinds of topics.
So the question is this one. So you verify your chips or whatever against some abstract properties, and do you anyhow verify the completeness of these properties against which you verify your systems? For example, if you take a property, so you say that, for example, given this and this input on your on the input sensors, there should be such and such output on this and this output sensors, to put it simply. So do you anyhow check that you cover all possible values spectrum for the input? And yeah, so does your property strong enough?
So the question is about, so in a DV, people have this clear notion, they have been matured over many years of coverage. And so, and when they have a high enough coverage, it's also an indicator that they've completed the job. Are there similar analogous notion of coverage for formal verification?
So, first of all, yes, there is coverage in formal verification. It's a lot more ambiguous term, but we are always trying to develop tools and better way to understand how good the quality is of what we achieve or what we do, and we developed different tools to reach that goal. Other than that, the basic, unlike dynamic verification, which is simulation generated, the assumption in formal verification is that we basically reach all the states. So I think it's less interesting.
No, but this is more coverage in the form of, have you written enough properties?
Well, also
so you can write a trivial property and you'll reach all the states, but the property says always true, right? You'll reach all the states. True. And so the question is, I think what you have in mind is, have you written enough properties?
If I've never written enough properties. So yes, we have a few systems to verify that. First of all, reviews. We go over our work and with other people, review what we've written and how we've written. Other than that, we have tools to cover exactly which parts of logic have been covered by our properties and which not. And we can see by that if we've covered most of the state machines.
There are some notion of people have attempted to define some notion of coverage that try to relate properties and state coverage. Completeness is maybe overloaded because you know, people are willing to have different notion of coverage, but it's somehow less comfortable to have different notion of completeness.
I just want to put in one plug here for vacuity, which I mentioned in my talk. It's trying to touch on a similar, maybe not the exact same problem, but on a similar problem. Are the properties that you've written, do they mean anything? Okay, because you could write properties that are meaningless, and that is something that vacuity tried to address.
And IBM has been really at the forefront of coming up with this concept and getting other people, myself and other people, to become interested in studying concept of vacuity. Vijay.
Great talks, thank you. So I have one question about SMT solvers. Are you familiar with them? And have you contemplated using them as opposed to, or in addition to SAT solvers?
Well, we have contemplated it, and we have not yet done anything about it.
Okay. And this comment was to answer your question about software verification. I think people are using SAT-based symbolic execution a lot to not necessarily to do verification, but to do testing in the software domain. And also people are using, so that's not as successful a story as hardware verification, but it's a start. Yeah, I will leave it at that.
I think today that at least a combination of concrete and symbolic techniques have become very standards in industry. There are different tools. I mean, this has become so not verification in the sense that you say yes, no, counterexample, but the use of formal techniques. And in fact, SAT solvers are used very, very heavily. There was a CSEM article a few years ago by Leonardo De Mura and Nikolai Bjorner about SMT solvers and how they are used, not exactly what we call model checking, but a whole slew of different tasks of software reliability are using SMT solver. Microsoft really has been forefront. As we talk now, there are probably hundreds of machines at Microsoft running SMT solver for industrial software development.
We are experimenting with SMT solvers. It's not yet production, but we're in advanced stages of using.
So can you tell us a fun story about a bug you found?
Okay, yes.
Mike.
I can. We were working on a chip that was interfacing with an Intel chip. And we had the Intel specification. And that's all we had. Our chip didn't exist yet. So we were building a model just to prepare for verifying it. And the specification was like it had tons of holes in it. We didn't know what should be. So any place where we didn't understand or we didn't know, we tried asking, but you know, they said this is the specification. And we put, so we put non-determinism. And we actually were able to prove, we modeled their chip. Anything we didn't know, we put non-determinism. And then we were able to show that actually whatever chip we made could never work. It was like not possible to interface with their chip. So we brought them a couple traces, kind of like counterexamples, and said, look, you can't do it this way, and you can't do it this way, and you can't do it this way. And finally they said, oh, you're right. That's what is in our spec is not the way we do it because it doesn't work. And do you have any more traces like these? Yes.
So I do not have.
I'll tell you a story of one of my early encounters. So there was a piece of logic that no one thought could be formalized. I'm talking about I don't know 8 years ago, and it has been running for a few projects, and everybody thought it was clean, and nobody could think about anything. Nobody could imagine that there were still bugs there, and I took on that project and took on that piece of logic, and after solving the problem and finding the way to do it, I found 2 bugs in that area, and that was very impressive using formal, and since then that was it was a transition. It was a transition between using a dynamic verification to check this piece of logic. Then from then only formal checked it, and since then for the last 8 years. So that was.
So actually, I will remind you a fun bug, and this had to do with what you describe. As you define the language, you have to be careful not to break the language, and one of which that we expected. That model checking tool will be, we expect them really, all of them run in exponential time, but we want to be in exponential time and not require more than that. And so at some point there was some additional feature, and IBM team seemed, we know how to do it in exponential time. And I end up saying, well, but you should look at Hopcroft and Ullman, page so-and-so, this problem is X space complete. Then there was silence for a few days, and then Sydney came back and says, we found a bug. And she coined a new phrase, complexity theoretic debugging. Was a question there?
So you've been talking in your formal verification teams, you always, yeah, so it's become uncomfortable even. So you have always formal methods experts doing formal verification, right? So how far are we, or is it even possible to have non-formal methods experts doing formal verification? In a sense, like completely automating all the stuff like artifact generation. Like we have, for example, non-skilled people in code writing, producing code via Simulink. Right? So you build design and you generate code. So like from your design generating a formal model which you can verify automatically.
So first of all, we don't have only formal experts doing formal. We do have more than 100 hardware designers who are using rule-based on their own logic. The thing is that when you have a non-expert doing it, they can take a smaller piece of logic, only because all of the tricks of how you do things, it's not that they're not capable, they don't have the time to put into it. It's not their main job. So it's just a matter of degree.
So in a sense, I believe, so from my Intel experience, I think that a lot of expertise is still needed, at least if we look to 5 years back. We had teams with PhDs on the validation side and not only on the tool side. I think on the new domains that I'm mentioning, from the modeling side, there are people that look to the modeling side could be from a different discipline. They do not need to have the same in-depth knowledge of the verification engines, but still system architects or designers could for sure leverage from the formal techniques. And I see that happening in GM. For sure, it is not like in hardware verification, it is not masses, but formal system architects using formal methods in order to model reactive systems.
Yeah, in Mellanox we've been trying this to give the designers tools, formal tools to use. It's a lot less effective, but especially designers use it when they don't have an available formal engineer to run it themselves. So it's not, it gets some result, but it's nowhere in the same vicinity of someone who really knows what he's doing.
Reactive synthesis, is it impossible dream, and what can we do to make it more feasible? So reactive synthesis means we have LTL properties and automatically generate a system.
I don't know if it's an impossible dream. It would be really, really cool if you could do it. We had some little projects at IBM, and you get interesting results. You probably understand you're very far away. But if you could do it, it would be really, really cool.
I have no idea.
What kind of properties do you write? So I understand that you use PSL in IBM, and what kind of temporal or non-temporal logics do you use for specifications? And even if you do use PSL, are most of the properties really complicated temporal logic, or more of assertions and very simple safety properties?
In Mellanox, we are we're barely using PSL. All we're using is basic assertions. The smartness behind the properties are in coding the way and not the actual PSL assertions. Although we do use some PSL assertions for verification, but mainly basic assertions.
We currently are not using the formal verification methods.
So, liveness versus safety. Where are we on this?
Safety.
Safety.
Hi. So, what do you think about how we should promote this formal verification technique among chip designers? Since from my experience, Verilog designers do not like to write assertions when they are writing their code.
Okay, so I have an answer now to Moshe's first question, which was what can we do in academia? And hardware designers are frequently very suspicious because they've never heard of it and they don't know what you're talking about. And if they get a first, if it's the first time they've seen such a trace and you made it an error in the environment, then they say, this doesn't work because they don't understand what's happening. So what you can do is have courses for hardware designers that are non-theoretical courses and that they learn this is a way to verify chips. And as people start coming up and understand it, people will be more accepting of it.
I think I've heard that in Technion there is such a course.
Yeah, but in computer science, and it's very difficult to teach it to electrical engineers.
Okay.
Because we count on logic, not the logic of a design, but mathematical logic very strongly. And in electrical engineering, they don't study. It's possible, but it's an effort to teach formal verification without any basis of mathematical logic. So right now they don't have any course.
Okay.
It would be nice.
They have probably for positional logic, right? Boolean logic.
Boolean logic.
Yeah, in Boolean logic you can always write assertions. Yeah. That's always possible. So you can teach it like, I'm an electrical engineer, you can teach electrical engineers to do formal. I just want to say it's all a matter of education. In Mellanox, designers do write assertions and many assertions, and they're very important. They're a major factor and part of in our verification process.
What I was thinking is I'm sure there are certain courses, maybe more in the graduate studies on the system design, software system design, that could use also STRL state charts and also come up with tools that show how to do those modeling and verification. So I believe there are certain courses, but I guess this could be also done more massively. So people are pretty familiar with those terms or with those systems, and just when they come to work, they feel comfortable applying it.
There is a phenomenon that what you studied in undergraduate, your undergraduate degree, that's okay, that's standard, everybody knows. Everything new is, oh my goodness, this is scary stuff. So in fact, one of the things that we have, one reason I think that one formal method is more heavily used, I think, in Israel than in other places, is the fact that we have courses in the Technion, even though it's only computer science and not you know, ECE, and there's a course here at the Hebrew University, and a courses in some places. So there are lots of people go to industry and they've heard a course about it, so it's not scary for them. They're willing to experiment with it. Yes, over there.
So is there some cooperation happening between like different companies applying formal methods, or is it just too specialized, too competitive?
I'm sorry, I was looking for your face, and so I didn't hear the question.
Sorry.
Once more.
Is there some kind of cooperation happening between different companies applying formal methods, or is it too specialized or too competitive?
Well, as an example, because your tool is used by many companies.
Yes,
right?
Mellanox is a customer of IBM. Many of our, I mean, there's a lot of people who've gone back and forth from Intel. I started at Intel. So there's cooperation because we know each other and because we are clients of each other, customers.
Yeah, I believe also on the formal specification languages that there were more of a collaboration in a way, kind of within Sugar and FSL, and kind of on the standardizations and
on the committees. Yeah.
On the committees, kind of.
Yeah, well, it's a small world, formal, and some people that worked under me and I trained work now in different companies. So the information does travel from company to company, and aside from that, there are some conferences dealing with specific issues throughout the year. But there's also a lot of expertise which is inside the company and stays as a knowledge base inside the company.
So a sociologist at Berkeley wrote a book some years ago trying to understand why Silicon Valley generally has been more successful than other high-tech centers. In particular, there's Route 128 around Boston that has not, early on it was a high-tech center, but did not thrive as much as Silicon Valley. And her conclusion was that the secret to the success of Silicon Valley was lack of loyalty. and there is a history there that one of the very, very first companies started in, semiconductor companies started in Silicon Valley was in the maybe 56, was Shockley Labs, started by William Shockley, was one of the inventor of the transistor. And so he was he received the Nobel Prize in physics, but he was a totally crazy manager. And then eventually some people, first of all, left his company and started Fairchild Semiconductors. And then they became unhappy with Fairchild, so they left Fairchild and started Intel. And that kind of became a pattern of behavior. I don't like this company, I'm going to go to another company. And companies at the beginning tried to use it, and they have gone to court to say, no, my employees should not be able to go to a competing company because they are carrying trade secrets. But eventually the courts went more for the freedom of occupation was stronger than your ownership of trade secrets. So people move a lot between companies. So it's very hard to keep these things. You know, I mean, if here you were at Intel, now you're at GM. Well, all the knowledge you got from Intel, you still have it in your head. The same thing, you were at Intel, you went to IBM. These people move around. I think Israel, there is a little less mobility than you find in Silicon Valley. But still, you know, I can think of many people from Intel that are now in different companies. Intel had fairly significant layoff. About 10% of the workforce was laid off about 2 years ago.
A year ago.
A year ago. And all these people now find other jobs in other companies. And all this knowledge that they had from Intel, they're going to take them to other companies. So there is collaboration, whether the companies want it or not.
I have a question. Okay.
Uh,
So in the universities, we are taught that.
One before the last question.
Okay. So in the universities, we are taught that dynamic verification cannot guarantee, but can only detect the bugs, and formal verification can guarantee this some properties. Even though this is true, but the verification tools are software themselves, and how much they are reliable, and what you do to guarantee the guarantee.
Who guards the guardians?
Yes, the tools are tools, and the tools have bugs, and we have bugs. With a formal verification tool, you actually find the bugs really fast. It's hard to make a bug in a formal verification tool that you're not going to find like the first or second thing you run on it. That being said, we have found bugs that have been there for a long time, and it's one of the reasons. There are many reasons why we say we do formal and we do dynamic, but I would never, ever, ever say that formal proves it's correct. For that reason, as well as many other reasons, including human error, and have I written enough properties? And it's a very, very strong tool. And it's not perfect.
I think formal is, as you said, for creative and very intelligent people, because the verification is very much based on what you are asking to verify. So.
I think there are a lot of systems to guard ourselves that's correct for every tool. A lot of the systems and processes that we do to verify that we did everything we planned to do, and all the tools worked accordingly, and everything is double checked and triple checked to make sure that there are no bugs no important bugs that disappeared.
Last question.
I would expect that the intent to formally verify something also affects the design. When the designers say, okay, let me tell you what I'm going to do here, just by saying it and formalizing it in some assertions and so on, he or she understands it better, maybe does it differently in preparation. Maybe you can elaborate on that.
Does the process of writing properties, does it help the designer conceptualize their design better and even find bugs even before they run any model checker, just by having to think more formally about it?
Was that your question?
Yes.
Yeah. Okay. I understood it differently. I'll let you answer.
So in my case, this is exactly what we do while we are designing the new communication languages and so forth, because currently we do not have a well-established process for verification. So we are using it as a design tool in order to reduce redundancy, in order not to create communication touch points that are redundant. So in this sense, we are, at least from my GM era, the use of formal methods is mainly from the modeling side, and to help the design of new languages in a way.
Let's thank the panelists for a very instructive panel.